It was April 10th, 2019, when the world gathered to see something that had never been seen before. On screens across the planet, a ring of light glowed faintly around a dark center. The image came from the galaxy Messier 87, 55 million light-years away, showing the shadow of a supermassive black hole whose mass equaled 6.5 billion suns. For the first time in human history, the universe revealed a place where light itself could not escape. The image was not a photograph in the ordinary sense. It was the result of years of coordination between scientists, engineers, and observatories scattered across the Earth. The project was called the Event Horizon Telescope, a name that reflected its impossible goal: to look at a region of space where looking itself becomes meaningless. No single telescope could ever resolve such detail. To see an object so small and so distant required something extraordinary. The team built a planet-sized eye. By linking radio observatories from Chile, Spain, Mexico, the United States, Hawaii, and the South Pole, they created a network capable of extraordinary resolution. Each telescope was synchronized using atomic clocks accurate to within billionths of a second. Together they formed what is known as very long baseline interferometry, a technique that allows multiple instruments separated by thousands of kilometers to act as a single telescope as large as the distance between them. The result was an effective resolution, sharp enough to see an orange on the surface of the moon. Yet what the world saw that April morning was not simply the raw image of a cosmic object. It was a reconstruction of signals, waves, not light in the visible sense, captured at a wavelength of 1.3 millimeters. The telescopes recorded the incoming radio waves on hard drives, which were later flown to a central facility where the data could be combined. Because even the slightest atmospheric distortion or timing error could ruin the entire image. Every fragment of data had to be precisely aligned and correlated. The effort took months of computation, calibration, and cross-checking. Each radio signal contained only partial information. It was like listening to scattered notes from a distant orchestra and trying to infer the full symphony. Using mathematical models and algorithms refined over decades, the researchers transformed the raw radio data into an image that corresponded to the intensity and distribution of emission around the black hole. The bright ring represented radiation from electrons spiraling through magnetic fields in the surrounding plasma. The darkness at the center was not a physical surface, but a shadow cast by the black hole's gravity. The term shadow can mislead. It is not cast on anything. It is the absence of light reaching us from certain directions because photons are either captured by the black hole or bent so severely that they miss the Earth. It is the silhouette of space-time curvature itself. What appears dark is where light falls inward, swallowed by an event horizon we cannot directly see. Behind the scientific precision of the image lies a quiet triumph of coordination. Each observatory faced its own weather, its own mechanical challenges, and yet all were united by a single goal: to capture the unseeable. The synchronization required that the entire planet act as one instrument, its parts connected by time measured not in human minutes, but in atomic oscillations. When the data were finally aligned, the shadow appeared. It had waited for eons to be noticed, and now, through patient ingenuity, the universe blinked back at us. The image, blurred and glowing, carried more information than its simplicity suggested. Scientists measured the size of the ring and compared it with predictions from general relativity. The match was astonishingly precise. The ring's diameter was about 2.5 times the event horizon's radius, exactly what Einstein's equations had predicted a century earlier. Within that agreement lay confirmation that gravity behaves as general relativity describes, even in conditions of extreme curvature. The achievement also redefined what an image means. This was not light reflected off a surface. It was the pattern left by radiation at the edge of a gravitational abyss, interpreted through mathematics and physics. What we saw was not the black hole itself, but the way space bent around it. The photograph was a map of distortion, a portrait painted by gravity. The process behind the image is as remarkable as its subject. The Earth's rotation allowed the telescopes to sweep across different parts of the sky, collecting a complete set of baselines as if a giant mirror had been rotated to capture every angle. When those signals were combined, the result was not a single snapshot, but a time-averaged reconstruction of billions of moments of radio light. Every pixel carried the imprint of both cosmic history and human patience. For many, the shadow symbolized mystery and awe. But for scientists, it was a measurement, a test, and a beginning. It confirmed that the equations of space-time remain trustworthy, where gravity is strongest. Yet it also reminded us of what lies beyond measurement, the region hidden behind the horizon, where even theory strains. The image, though celebrated, was still incomplete. In the quiet after the announcement, one could sense the deeper question forming beneath the applause. If we have finally seen the shadow of a black hole, what have we truly seen? And what remains hidden within that darkness that no telescope, no matter how vast, can yet reveal? The moment the image appeared, a century of theory became something the eye could finally grasp. For generations, physicists had described the mathematics of curved space-time, but no one had witnessed it so plainly. In the bright ring around the black hole in Messier 87, Einstein's equations were no longer lines on paper. They were glowing arcs of plasma following invisible geodesics in the geometry of the universe. What we had captured was not an object, but the consequence of gravity itself. Every particle of light seen in that image had traveled across 55 million years of cosmic distance. Through clouds of intergalactic gas, through the thin air of the Earth's atmosphere, across the vastness between galaxies, each photon carried a story of being bent, delayed, and red-shifted by gravity. By the time it reached the telescopes, it had been transformed by the very forces it revealed. To look at the image was to look backward through both space and time, seeing light that had begun its journey when early primates first walked upright on Earth. What gave the ring its brightness was motion, matter orbiting at nearly the speed of light. Near a black hole, gravity pulls so fiercely that matter cannot fall straight in. Instead, it spirals, forming an accretion disk where magnetic fields twist and tear through plasma. The electrons caught in these fields emit synchrotron radiation, their energy released in radio waves. The Event Horizon Telescope tuned precisely to those waves, revealing a luminous outline around the void. One side of the ring appeared brighter because the plasma there was moving toward us. Relativistic Doppler effects intensified its light, while the opposite side, moving away, appeared dimmer. The asymmetry itself was a signature of motion near light speed, just as predicted. At first glance, the ring seems to surround a black circle, but that darkness is deceptive. The shadow is not the event horizon. It is a region roughly 2.5 times larger, defined by the photon sphere, where light can orbit the black hole in unstable loops. Any photon crossing that boundary either escapes to infinity or plunges inward forever. The shape and size of the shadow depend on the black hole's mass and spin. By measuring its diameter, scientists could infer how massive it was, confirming calculations made decades earlier through the motion of surrounding stars. Even the blur of the image was meaningful. Interference patterns, atmospheric noise, and sparse telescope coverage could have distorted the reconstruction. Yet the ring's symmetry and scale persisted through every algorithm tested. The image was rebuilt using several independent methods to ensure no human bias shaped it. Each approach, from maximum entropy reconstructions to Bayesian modeling, produced the same unmistakable ring. The convergence of methods strengthened confidence that what we saw was real, an astrophysical structure, not a trick of mathematics. The challenge of turning data into an image required more than computing power. It demanded patience with the universe's indifference. Clouds over Chile, humidity in Hawaii, snowstorms at the South Pole. Each local condition threatened to break the global synchronization. The team had to wait for perfect alignment, when weather and technology conspired to open a narrow window of clarity. In those moments, the Earth became a single lens, focused on a galaxy millions of light years away. When the raw data were finally combined and calibrated, the first reconstructions appeared on screens inside the analysis rooms. Scientists who had spent years doubting whether such an image was even possible stared at the faint ring in silence. It looked almost too familiar, too perfect, like something their equations had drawn long before. The curvature of space-time, the bending of light, the existence of the event horizon, all encoded within that blurred circle. But science demands humility, even in triumph. The shadow, though breathtaking, was a surface-level truth. It revealed what gravity does to light, but not what lies within the darkness itself. The event horizon, by definition, conceals everything beyond. To call the image a photograph of a black hole is convenient, but not precise. What we saw was a shadow shaped by photons that narrowly escaped destruction, not a glimpse of the void's interior. Still, the accomplishment transformed our understanding of observation. Until then, black holes had been inferred only through motion. Stars orbiting unseen centers, jets of energy streaming from invisible points. Now, the invisible had a visible boundary. The concept that began as a mathematical curiosity in 1916 had, through human persistence, become an observed feature of the cosmos. For the first time, humanity had seen a place where time slows to near stillness, where escape is impossible, and where the laws of physics reach their limits. The shadow on our screens was a message written in light and gravity, a confirmation that the fabric of space-time can indeed curve back upon itself. But every revelation conceals a deeper question. If this is what we can see at the very edge of visibility, what truths lie hidden beneath it? If light can orbit a black hole, can information do the same? And if the shadow matches our predictions so perfectly, does that perfection mask something we still do not understand? To look at that glowing ring is to glimpse the boundary between certainty and speculation. What lies beyond the shadow is not simply darkness, but the failure of every instrument and equation we have built to describe reality. The black hole in Messier 87 stands as both a confirmation and a challenge. It confirmed that Einstein's description of gravity works even under the most extreme conditions known. But it also reminded scientists that the theory, however elegant, cannot penetrate what lies beyond the event horizon. There, our mathematics encounters infinities and undefined quantities, signs not of deeper truth, but of the limits of human understanding. For the astronomers who worked on the Event Horizon Telescope, the image was not an ending. It was the beginning of a new type of measurement. By observing at 1.3 millimeters, they had tuned their vision to see through the thick fog of dust and plasma that usually hides galactic centers. The choice of wavelength was deliberate. Longer waves would blur the image, and shorter ones would be absorbed by the atmosphere. At 1.3 millimeters, the signal could slip between those barriers, carrying information from a region where gravity, magnetism, and velocity intertwine. Each bright photon detected by the telescopes represented energy released as matter spiraled inward. The light we saw was the last scream of falling gas, heated to billions of degrees as magnetic turbulence twisted it into knots. Near the event horizon, time and space exchange roles. Distance becomes time, and time becomes direction. What appears to us as a stationary ring is, in reality, an inferno of motion, where matter orbits hundreds of times per second before vanishing into silence. The shadow does not flicker, because the average of that chaos forms a stable pattern. It is a stillness born of furious speed. In this sense, the image captures more than a black hole. It captures the cooperation between nature's most violent engine and the delicate instruments built by humans. Each bit of data on those hard drives traveled from mountaintops and deserts through cold air and vacuum-sealed containers until they met in a laboratory where time itself was aligned down to a fraction of a microsecond. The synchronization was so precise that the slightest drift would have erased the image entirely. In those measurements, one can feel the fragility of human knowledge, that our understanding of the cosmos depends on aligning moments perfectly across a spinning planet. And yet, for all its technical achievement, the image left the same unanswered question that has haunted physics for decades. What, exactly, defines the edge of a black hole? The shadow tells us where light fails to escape, but it says nothing about what happens to the information carried by matter that falls in. The Event Horizon Telescope revealed the outer geometry of gravity's trap, but its interior remains silent. It is a silence not of ignorance, but of principle. No signal can cross that boundary to return a message. Still, the human mind refuses to accept silence as an answer. From the moment the image was released, theorists began comparing it to models that tested general relativity against alternatives, exotic possibilities like gravitar stars or wormholes. None matched the data as well as Einstein's theory. Within the ring's perfect roundness, relativity stood unbeaten, but that perfection itself inspired discomfort. Nature rarely offers flawless symmetry. Perhaps the simplicity hides complexity we cannot yet detect. Perhaps the universe is whispering that the truth lies deeper, behind the shadow we now so proudly display. For the world, the image became an icon, proof that humanity can reach across galaxies with instruments of reason. But for science, it became a calibration point, a test to refine and question. Every pixel of that ring is now measured, modeled, and compared against simulations that predict how black holes should behave. Already, plans are underway for future observations at shorter wavelengths and with more telescopes to see motion within the accretion disk itself. The goal is to turn the still picture into a movie of space-time twisting around the abyss. And so the chapter of discovery that began in April 2019 continues. The image of the shadow is no longer just a symbol of what we cannot see. It is a doorway into questions that may one day lead beyond the limits of general relativity into the uncharted territory where quantum mechanics and gravity converge. For now, the shadow remains what it has always been, a silence surrounded by light, a shape drawn by the absence of escape. We have seen it, measured it, and confirmed its place in the cosmos. Yet in doing so, we have also seen the edge of our own comprehension. Beyond that ring lies not myth or imagination, but the simple fact that the universe still holds secrets larger than our theories. The black hole's shadow is the outline of our curiosity. It is the mark left when knowledge meets its horizon. What we captured on that day was not the darkness of destruction, but the boundary of possibility itself. The world called it a photograph of a black hole. But that phrase is only partly true. What the Event Horizon Telescope revealed in April 2019 was not a direct view into the abyss, but a carefully reconstructed map of radio waves emitted by matter orbiting near the point of no return. The dark center is not the black hole itself, nor even the event horizon. It is the photon capture region, a space about 2.5 times larger than the horizon, where light is trapped in unstable circular paths before falling inward. What we saw was not the black hole, but its influence on light. To understand that, one must look through the language of general relativity. In Einstein's framework, gravity is not a force pulling on objects, but a warping of space-time caused by mass and energy. When light passes near a massive body, it follows the curved geometry rather than a straight line. Near a black hole, that curvature becomes so extreme that light can circle the object many times before escaping. The boundary of those looping paths forms what scientists call the photon sphere. The dark region at the center of the image represents the directions from which no photons reach us, a shadow cast not on any surface, but upon the fabric of space-time itself. Around this shadow, we see a ring of light glowing orange in the reconstructed image. That glow is synchrotron emission. radiation from electrons spiraling along magnetic field lines in the hot plasma that swirls around the black hole. These electrons move close to the speed of light, and their energy is released as radio waves at the wavelength observed by the Event Horizon Telescope. The bright arc is not uniform. One side of the ring shines more intensely because the plasma there is moving toward Earth. At such high speeds, special relativity predicts that light emitted in the direction of motion becomes amplified. The opposite side, moving away, appears dimmer. This asymmetry gives the ring its crescent-like appearance and encodes the direction of the black hole's rotation. Every element of the image carries a physical explanation. The thickness of the ring, its brightness, and its slight offset from the center all correspond to the geometry of the system. By comparing these features to models built from Einstein's equations, scientists determined that the black hole in Messier 87 must be spinning, though not at its maximum possible rate. The precise orientation of its spin axis, nearly perpendicular to our line of sight, explains why we observe powerful jets of plasma shooting out from the galaxy's core. Those jets, seen in radio and optical observations, are streams of matter accelerated by magnetic fields near the black hole's poles, evidence that gravity and magnetism cooperate in ways still not fully understood. The image's dark region is not a void, but a prediction confirmed. The size of the shadow matched the radius expected for a black hole with 6.5 billion solar masses. That agreement within 10% was not a coincidence. It was an experimental validation of general relativity on galactic scales. When the theory was first proposed in 1915, there was no way to test it under such extreme conditions. Now, more than a century later, the bending of light near a black hole has been observed exactly as the equations describe. To the untrained eye, the image might appear like an abstract pattern, but to physicists, it is dense with meaning. It tells them about the curvature of space-time, the behavior of plasma under immense gravity, and the way magnetic fields organize near the edge of a singularity. Each of these insights emerges from the brightness distribution across that ring. By fitting the data to simulations of accretion disks, researchers can infer temperature, density, and flow patterns in the gas orbiting near the horizon. What they found confirmed that this region is not chaotic in the ordinary sense. It follows stable, predictable structures shaped by magnetohydrodynamics, the physics of charged fluids in magnetic fields. The Event Horizon Telescope team tested their results with rigorous skepticism. They created synthetic datasets, deliberately scrambled inputs, and blind analyses to ensure no one's expectations could influence the outcome. They divided into multiple groups that worked independently, each using different algorithms to reconstruct the image. When the final results were compared, the same ring appeared again and again. Its size, orientation, and asymmetry remained consistent. Such repetition across independent methods strengthened confidence that the structure was real. To see what we saw was to witness gravity bending light into a circle. Photons that began their journey in every direction were curved by the black hole's mass until they formed a luminous boundary around darkness. The ring itself is a projection, a two-dimensional imprint of a three-dimensional process. Its shape would appear nearly circular from any viewing angle because the gravitational field around a rotating black hole distorts light in just such a way. Even though we cannot see the event horizon directly, its presence shapes the very geometry of what we observe. This revelation deepened the mystery rather than solved it. The shadow confirmed that black holes exist, but it also made clear that we cannot yet peer beyond their surfaces. All we can measure is how they affect the light escaping from the brink. What we call an image of a black hole is, in truth, an image of how space-time itself behaves near its limit. It is a mirror reflecting the laws of physics back at us. As the world celebrated the photograph, astronomers quietly reminded each other that the shadow is not the end of discovery. It is the start of a new era of measurement, a gateway to testing relativity, plasma physics, and even quantum theories of gravity. What the Event Horizon Telescope captured is a frozen frame in a dynamic story. one that continues to unfold as the black hole consumes and radiates energy in ways we are only beginning to understand. The universe had offered a glimpse of its most hidden structure, yet what we saw was not the black hole's heart, but the echo of light escaping its pull. The image told us that gravity bends light exactly as predicted, but to grasp what that means, to understand the true depth of that darkness, we must trace how such cosmic monsters come into being. Stars are born in clouds of gas and dust, but their deaths are far more dramatic. To understand what we truly saw in that image from Messier 87, we must trace the story backward to the moment when gravity overcomes every opposing force. The shadow we observed is the final stage of a process that begins in the cores of massive stars, where nuclear fusion holds gravity at bay for millions of years. Inside such a star, hydrogen fuses into helium, and the energy released pushes outward, balancing the relentless inward pull of its own mass. But balance is temporary. When the fuel runs out, the furnace cools, and gravity reclaims its dominance. For stars with several times the mass of our Sun, this collapse is unstoppable. The core contracts until the electrons are crushed into protons, forming neutrons. The outer layers rebound in a supernova explosion, scattering the heavy elements that later form planets and life. What remains is a neutron star, an object so dense that a teaspoon of its material weighs billions of tons. Yet even neutron stars have a limit. If the remaining core is heavier than about 3 solar masses, even neutron degeneracy pressure, the quantum force that keeps neutrons apart, cannot resist gravity's pull. The collapse continues without end, compressing matter into a point of infinite density. In that instant, a black hole is born. This idea was not new when the Event Horizon Telescope made its discovery. More than a century earlier, in 1916, Carl Schwarzschild had found a solution to Einstein's field equations, describing how space-time behaves around a perfectly spherical mass. His work, written while he served on the front lines of the First World War, revealed a curious radius where the equations seemed to break. At that radius, now called the Schwarzschild radius, time and space swap roles. Inside it, every path leads inward, and escape becomes impossible. For decades, physicists debated whether such regions could exist in nature or were merely mathematical artifacts. In 1939, J. Robert Oppenheimer and Hartland Snyder published the first realistic model of a star collapsing under its own gravity. They showed that if the mass were large enough, no known force could halt the collapse. From the outside, the process would appear to freeze in time. Light emitted from the falling surface would grow dimmer and redder. Its wavelength stretched endlessly as time slowed. To a distant observer, the star would fade into darkness, leaving only its gravitational influence. It was the first theoretical glimpse of what we now call the event horizon. Decades later, evidence began to build that such objects were not merely theoretical. In the 1960s and 70s, astronomers discovered compact sources emitting powerful X-rays. The motions of nearby stars suggested invisible companions with masses too great to be neutron stars. These were the first clues that black holes might populate our galaxy. By the late 20th century, attention shifted to something even larger: the supermassive black holes that anchor galaxies themselves. Measurements of stellar orbits near the center of our Milky Way revealed a mass of about 4 million suns confined within a region no larger than our solar system. There could be no other explanation consistent with physics. The same pattern appeared elsewhere, in Andromeda, in Centaurus A, and most dramatically, in Messier 87. The black hole in Messier 87 dwarfs all others we have studied. Its mass equals billions of suns, and its gravitational influence shapes the motion of an entire galaxy. Jets of plasma, thousands of light years long, stream from its poles, visible across the electromagnetic spectrum. The power driving those jets originates not from the black hole's interior, but from the energy of infalling matter and the magnetic fields that thread through it. The very same forces that produce those distant jets also shape the glowing ring captured by the Event Horizon Telescope. When we look at the shadow, we are seeing the final product of stellar death and cosmic evolution. Every black hole, whether born from a collapsing star or grown over billions of years through mergers and accretion, carries within it the history of matter transformed by gravity. The darkness at the center of the image is the endpoint of that transformation, the point where the universe's geometry becomes so curved that light itself cannot climb out. To scientists, the image from 2019 is a bridge between theory and evidence. It connects the mathematics of collapse with the observable universe. What began as equations scribbled in wartime notebooks now glows in radio waves from a galaxy 55 million light-years away. The chain linking those ideas, from Einstein and Schwarzschild to Oppenheimer and Snyder, and now to the Event Horizon Telescope, spans more than a century of relentless curiosity. Yet even this triumph leaves us on the edge of understanding. The image confirms that massive collapse leads to the structures Einstein's equations predict, but it tells us nothing about what happens inside. There, the known laws of physics cease to describe reality. The densities become infinite, and space-time itself seems to tear apart. If the shadow shows us the exterior of gravity's masterpiece, then the interior remains an unfinished chapter in our understanding of nature. The story of the shadow, therefore, is not only about what we observed, it is about the long history of human attempts to comprehend how light, matter, and time themselves respond when pressed to their limits. The image from Messier 87 stands as a symbol of this journey, a confirmation that the universe obeys the same mathematics everywhere, and a reminder that our knowledge, like light near the horizon, is always bending towards something we cannot yet see. The discovery of the black hole's shadow confirmed more than Einstein's equations. It redefined what it means to observe. Until the Event Horizon Telescope, every image humanity had taken was formed by light reflecting off surfaces or scattering through matter. But the shadow of Messier 87 was different. It was not reflected light at all. It was radiation emitted by particles tracing the invisible geometry of space-time. What appeared on our screens was not an object, but a map of motion, a record of light, twisted by gravity and frozen in time by computation. In this way, the image became a kind of mirror, showing not the black hole itself, but the precision of human understanding. The clarity of that ring proved that nature is not chaotic even at its extremes. The behavior of matter near a black hole follows rules so exact that computer simulations, run years before the observation, predicted almost every feature we later saw. The ring's thickness, its brightness asymmetry, and even its near-perfect circularity all matched models derived from general relativity and plasma physics. Within a 10% margin, the measured diameter of the shadow aligned with the theoretical expectation for a 6.5 billion solar mass black hole. The agreement was almost unsettling, as if the universe were holding up a chalkboard filled with equations and saying, yes, this is correct. Yet beneath that satisfaction lay unease. Every confirmation carries an implication. If our theories describe everything we can observe so precisely, they also highlight the limits of what we cannot. The image reveals the geometry of space-time just outside the event horizon, but it cannot tell us what happens at the boundary itself. The horizon remains a one-way surface, its inner reality concealed not by distance, but by the laws of causality. Even light cannot return a message from within. What the Event Horizon Telescope gave us then was not direct sight into the black hole, but the best possible evidence of its existence and its obedience to known physics. Still, the fact that such precision was possible is astonishing. The black hole's immense gravity warps not only space, but time itself. To the material swirling around it, moments pass differently than they do for us. Near the horizon, seconds stretch into hours. and hours into centuries. What appears to us as a steady, glowing ring may in fact be a rapidly shifting storm of plasma. Its flickers slowed by relativity until they merge into an almost constant halo. The image is a time average, a portrait of motion that has been smeared across the dimension of time itself. The Event Horizon Telescope team understood this deeply. They did not mistake the still image for a static object. Instead, they used it as a snapshot from a dynamic system. Already, plans were underway for future arrays that would observe the same black hole over time, turning that frozen frame into a movie of matter orbiting near light speed. Each pixel of that future movie would reveal how energy and magnetism behave when confined by gravity's most extreme curvature. In that sense, the image we saw in 2019 is the first frame of an ongoing experiment, one that will continue for decades. Among the most remarkable outcomes of the observation was how accurately it tested the symmetry of general relativity. If black holes were somehow different from what Einstein predicted, if their horizons had irregularities, or if space behaved unexpectedly near their edges, the shadow's shape would have revealed it. Even tiny deviations would distort the circle into an ellipse or an uneven arc, but no such distortion was found. The shape was circular to within a few percent. It told physicists that space-time, even under unimaginable pressure, follows the same smooth geometry that the equations demand. And yet, this same perfection deepens the enigma. For if relativity holds absolutely, then the singularity predicted at the black hole's center must exist, a point where density becomes infinite and our mathematics breaks. We have confirmed the edges of Einstein's masterpiece, but are forced to admit that the core of it remains a mystery. The black hole's shadow, therefore, is not only a test of our understanding, but a challenge to surpass it. As the celebration faded, scientists turned their attention to what the image did not show. The event horizon itself remains invisible. The inner accretion disk, where matter plunges inward and magnetic turbulence roars, cannot yet be resolved. Even the polarization of the light, the twisting of its electric field by magnetic forces, required later observations, published 2 years after the first image. Those follow-up results hinted at ordered magnetic fields powerful enough to launch the galaxy's colossal jets. But even they could not reveal how matter truly crosses from our universe into the region beyond return. In the end, the black hole's shadow stands as both proof and paradox. Proof that our theories can describe nature with astonishing precision, and paradox because that very precision leads us to the boundary where those theories fail. The image is a cosmic reflection of human limitation. We see the structure of space-time itself, yet the one place where space-time ends remains hidden. To say that we have photographed a black hole is therefore both true and false. We have seen the evidence of its presence, the trace of light shaped by its gravity, the ring that marks the border of no escape. But what we truly saw was the effect of the unseen, the imprint of an object defined not by what it emits, but by what it withholds. The ring of Messier 87 is a window that looks inward and finds not a surface, but an idea. It is a sign that general relativity holds in the real universe, and a whisper that there is still more to learn beyond its reach. If the image told us what gravity can do to light, then to understand its depth, we must look at how black holes themselves come into existence. For behind every shadow lies a collapse, a moment when matter falls inward and time, as we know it, begins to lose its meaning. In the life of a star, gravity is both creator and destroyer. It gathers clouds of hydrogen into spheres of fusion, and when that fuel is gone, it brings those same spheres to ruin. The story of every black hole begins with this ancient balance between pressure and collapse, a balance that, once broken, sets in motion one of the most violent transformations in the universe. What we saw in the shadow of Messier 87 was the final echo of such transformations, magnified to galactic scale. But to truly understand that image, we must trace gravity's work back to its smallest and most relentless form, the death of a star. A star spends most of its life in a state of equilibrium. Deep in its core, nuclear fusion fuses hydrogen into helium, releasing energy that pushes outward against the inward pull of its own mass. This outward pressure keeps the star stable for millions or even billions of years, depending on its mass. The more massive the star, the faster it burns through its fuel. When the hydrogen runs out, the balance falters. The core contracts, temperatures soar, and heavier elements begin to fuse, helium into carbon, carbon into oxygen, and so on, layer by layer, like the shells of an onion. But even fusion has limits. Once iron forms in the core, the reactions stop producing energy. Fusing iron consumes energy instead of releasing it, and the equilibrium that kept the star alive finally collapses. In a fraction of a second, the core implodes. The outer layers crash inward and rebound in a shockwave so powerful that it can outshine an entire galaxy for days. This is a supernova, the most spectacular death a star can have. For a brief moment, gravity and pressure engage in a battle of unimaginable violence. What remains after the explosion depends on how much mass was left behind. If the collapsed core weighs less than about 1.5 times the mass of our Sun, it becomes a white dwarf, a cooling ember held up by the quantum pressure of electrons. If it is heavier, up to about 3 solar masses, the collapse continues until protons and electrons combine into neutrons, forming a neutron star. In that dense sphere, the matter of mountains is squeezed into volumes no larger than a city. The pressure of neutrons themselves resists further collapse, and the star stabilizes again, though at a cost. Its surface gravity is so immense that a single step would carry you to escape velocity, and its magnetic fields can whip through space with lethal force. But if the remnant exceeds that threshold, the Tolman-Oppenheimer-Volkoff limit, even neutron pressure cannot hold back gravity. The core's collapse becomes unstoppable. No known force can resist it. The equations of general relativity predict that the matter will continue to fall inward until it reaches a point of infinite density and zero volume, a singularity. Space and time themselves are dragged down into this abyss, forming what we call a black hole. The boundary that separates it from the rest of the universe is the event horizon, a one-way surface where the escape velocity equals the speed of light. The idea that such objects could exist first emerged from the mathematics of Einstein's field equations. In 1916, only months after general relativity was published, Carl Schwarzschild found a solution describing the curvature of spacetime around a point mass. His equations revealed a peculiar radius where time appeared to stop. Later, in the 1930s, J. Robert Oppenheimer and Hartland Snyder showed that a massive star collapsing under its own weight would form precisely such a region. They described how, to a distant observer, the collapse would appear to slow and freeze as the star's light grew infinitely redshifted. From that perspective, the star would seem to hover on the edge of visibility, never quite disappearing. Yet for the star itself, time would continue, carrying it beyond the horizon in a finite instant. These early insights were purely theoretical. For decades, black holes existed only on paper, dismissed by many as mathematical curiosities. Einstein himself doubted that nature would permit such extreme structures. But as the century progressed, observations began to align with theory. Astronomers detected unseen companions tugging on visible stars, their gravitational pull betraying immense masses in tiny volumes. Later, the discovery of quasars, brilliant, compact sources emitting more energy than entire galaxies, revealed engines that could only be powered by supermassive black holes feeding on surrounding gas. The turning point came with the study of the Milky Way's center. By tracking the orbits of stars near the radio source known as Sagittarius A star, scientists measured the mass enclosed within their paths. It was about 4 million times the mass of the Sun, confined within a region no larger than our solar system. Nothing but a black hole could fit those parameters. Similar measurements in other galaxies showed the same pattern. The presence of supermassive black holes was no longer speculation. It was a universal feature of galactic architecture. The black hole in Messier 87 sits at the pinnacle of this cosmic hierarchy. Its mass, 6.5 billion times that of the Sun, means that it formed not from a single collapsing star, but from the merging and growth of countless smaller black holes over cosmic time. It has been feeding on gas and dust for billions of years, sculpting its host galaxy through the immense energy released by infalling matter. The bright jets that extend thousands of light years from its poles are powered by magnetic fields twisting around its spinning horizon. What the Event Horizon Telescope captured in 2019 was not the formation of such a monster, but its enduring presence, a living remnant of gravity's endless appetite. Each black hole, regardless of its size, tells the same story: gravity wins. It is the one process in the universe that requires no external trigger. Left alone, matter collapses. Left alone, light curves inward. Left alone, space itself folds. The formation of a black hole is gravity taking its final form, not as a force acting within space, but as a curvature so deep that space and time merge into a single downward direction. The shadow we saw around Messier 87 is therefore the outer face of collapse, frozen in time. It is not an image of destruction, but of completion. It marks the boundary where matter ceases to exist as matter and becomes geometry itself. The light that escapes from that edge carries the signature of a process that has been repeating across the cosmos since the first stars burned out. Every black hole is a fossil of collapse, and every shadow is its enduring trace. If we could look beyond that shadow, we would see not chaos, but order, the deterministic flow of space-time folding around mass. The very laws that describe the fall of an apple also describe the fall of light into a singularity. The difference is only one of degree. In that sense, the black hole is not a break in physics, but its ultimate expression. Gravity, left unchecked, curves the universe into darkness, and yet from that darkness comes the light that allows us to see it. In the moments after a massive star collapses, time and energy lose their familiar meanings. The explosion of the outer layers races outward, lighting up space with the brilliance of 100 billion suns, while the core falls inward faster and faster, compressing itself beyond the reach of known physics. From the outside, the event lasts only seconds, but to the infalling matter, time slows until each instant stretches infinitely. The black hole is born in that slow fall, a place where the story of matter ends and the story of space-time begins. When we imagine a black hole, it is tempting to picture a cosmic drain, a whirlpool pulling everything toward its center. The reality is subtler and far more profound. Nothing physically sucks matter in. Instead, space itself is being pulled inward. The geometry of space-time curves so deeply that every possible path, even those light could once follow outward, now bend back toward the center. This is not motion through space, but motion of space. The black hole does not sit inside the universe as an object. The black hole is a region of the universe where the directions themselves have changed. Inside that region, every path leads to tomorrow's center. The precise shape of this geometry depends on how the black hole spins. A non-rotating one, described by the Schwarzschild solution, has a perfectly spherical horizon. But in nature, few things remain still. Most black holes spin, formed from collapsing stars that rotated or grown by matter spiraling inward over eons. When spin enters the picture, space-time becomes twisted. The solution that describes this, found by Roy Kerr in 1963, predicts a phenomenon called frame dragging. Near a rotating black hole, space does not merely curve. It begins to swirl, pulled around by the rotation of the hole itself. Even light, which normally moves in straight lines, must twist in the direction of that spin. This dragging of space-time means that nothing can remain completely still near the horizon. Every particle, every photon, is caught in the rotation. It is as if the fabric of reality has become a vortex, carrying everything forward. For an external observer, this manifests as the distortion we see in the shadow. The brighter, crescent-shaped side where plasma races toward us, its light boosted by the Doppler effect, and the dimmer side where it recedes. That asymmetry is more than a visual detail. It is the fingerprint of a rotating Kerr black hole. The equations describing this geometry are elegant and unforgiving. The Schwarzschild metric for a non-rotating hole can be written in simple form, showing how time slows and space stretches as one approaches the horizon. The Kerr metric, however, adds complexity, a term that represents angular momentum. This rotation creates two horizons instead of one, an outer event horizon and an inner boundary known as the ergosphere. In the ergosphere, space is dragged so quickly that nothing can remain motionless relative to the distant universe. Within it, particles can still escape if they move in the direction of rotation, and under special circumstances, they can even extract energy from the black hole's spin, a process known as the Penrose mechanism. This may be one of the ways nature powers the colossal jets we observe shooting from galactic centers. The Event Horizon Telescope's image of Messier 87's black hole bears the imprint of this geometry. The brightness gradient across the ring is not random. It aligns with the predicted direction of the black hole's spin and the orientation of its magnetic field. Even without seeing the interior, we can infer how space-time behaves there. The match between observation and theory is so precise that it stands as one of the strongest confirmations of general relativity ever achieved. Yet this precision carries irony. We know the equations describe the outside of the black hole perfectly, but inside, they lead to infinity, a place where they fail completely. The paradox is that the same mathematics that predicted the black hole's existence also predicts its own breakdown. At the singularity, density becomes infinite, and the curvature of space-time diverges. In physical terms, this means our theories no longer apply. It is a boundary, not of nature's making, but of ours. Every time the Event Horizon Telescope confirms general relativity, it also tightens the ring around this unsolved problem. Still, the process of collapse and the structure it leaves behind are real, measurable, and astonishingly consistent. When two black holes merge, an event detected through gravitational waves by the LIGO and Virgo observatories, the signals follow the precise patterns predicted by relativity. The final black hole's mass and spin can be calculated from the energy radiated in those waves. Each detection is another data point affirming that gravity's collapse behaves exactly as Einstein's equations dictate. It is humbling to realize that what we call a black hole is not a thing, but a region, a condition of space-time defined by geometry rather than substance. There is no material surface, no solid edge, only a horizon that behaves as if it were one. Matter does not pile up there. It disappears from our universe's observable domain, leaving behind its mass, charge, and spin as the only information we can detect. The simplicity of these remaining traits, known as the no-hair property, gives black holes their almost featureless perfection. Through collapse, the universe turns complexity into simplicity. A star's tangled interior, its layers of fusion and convection, its turbulence and magnetism, all vanish into three numbers. The black hole that remains is not an object, but an equation made real. It is gravity distilled to its purest form. The image of Messier 87's shadow, then, is not a photograph of a dying star, but the fossil of a process that began long ago and repeats everywhere gravity grows strong enough to devour itself. Each time we look at that ring, we are seeing the same story written in space-time's deepest language, the story of collapse, completion, and the enduring rule of geometry. To stand at the edge of a black hole, even in thought, is to witness gravity's ultimate expression. the moment when the stage of the universe bends beneath its own play. As a star collapses, it does not simply compress into smaller space. Space itself folds around it, changing the very rules that define direction and distance. What remains is not a physical body in any traditional sense, but a distortion of geometry so complete that all paths lead inward. This transformation does not happen in an instant, yet from a distance, it appears timeless. For the universe beyond, the collapse freezes on the edge of visibility, the last flicker of light slowing, stretching, and vanishing, as though time itself has forgotten how to move. That illusion arises from the way general relativity connects motion and time. To an observer falling with the collapsing matter, nothing unusual occurs when crossing the event horizon. The journey feels smooth, guided by the curvature of space-time, with no visible boundary marking the point of no return. But to a distant observer, light emitted from the falling material must climb an ever-deepening gravitational well, losing energy and stretching into longer wavelengths. Its color reddens beyond visibility, and its signal slows until it seems to stop. The star's death becomes eternal to those watching from afar, though to the infalling matter, it ends in finite time. This discrepancy lies at the heart of why black holes are both mathematically consistent and emotionally unsettling. They remind us that reality depends on where one stands in space-time. When Einstein first proposed general relativity, he could not have imagined that his equations would describe such regions, yet they do so perfectly. The geometry of collapse, predicted purely from mathematics, now mirrors what we observe through instruments spread across the Earth and orbiting above it. Even the gravitational waves detected from merging black holes bear the exact frequency and decay patterns predicted by relativity. Each detection is like a heartbeat from the cosmos, confirming that space and time are behaving precisely as the equations insist. But to understand why this happens, we must look at how gravity works in its purest form. In Newton's time, gravity was a force acting across space, pulling objects together. In Einstein's view, gravity is not a force at all, but a property of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. A black hole is the result of this dialogue taken to its extreme. When a star's mass is concentrated tightly enough, the curvature becomes so steep that no line, not even the path of light, can escape. The region inside the event horizon is cut off from the rest of the universe, a self-contained geometry where all roads lead inward and none outward. In the language of relativity, we could describe this using the Schwarzschild metric, which defines how space and time change as one approaches the event horizon. Time slows, space stretches, and radial distances no longer behave intuitively. Near the horizon, the difference between forward in time and downward in space disappears. The coordinates we use to describe motion outside the hole lose meaning inside it. There is no standing still within a black hole. Existence becomes motion toward the singularity, a one-way descent that defines the arrow of time itself. This collapse is not just an event in space, but a transformation of causality. Every particle's future is now directed inward. Nothing within that region can influence the universe outside. In that sense, a black hole acts like a cosmic boundary, a surface where information enters but never returns. It is both part of our universe and separated from it, a horizon of events, named so because no event occurring within can ever be seen again. The Event Horizon Telescope, in its name, acknowledges this truth. It does not photograph the whole, but the horizon's shadow, the last visible imprint of light that almost escaped. Even as the mathematics describe these processes precisely, they leave unanswered questions. What happens at the singularity, where density becomes infinite? Does space-time truly end there, or do quantum effects alter the outcome? No observation yet can tell. What we know is that collapse, once begun, is irreversible. The black hole does not simply consume matter, it absorbs the geometry that once supported that matter. In its place remains a perfectly curved void whose boundaries obey every rule we have tested. The black hole's formation is not the end of a story, but the beginning of a new one. Once created, it persists. Over cosmic time, it can merge with others, grow by feeding on surrounding gas, or drift quietly through space. In the centers of galaxies, supermassive black holes act as engines of evolution, shaping the stars and gas around them. Their gravity guides the motion of entire galactic systems, anchoring cosmic structures that span millions of light years. The same process that begins in the death of a star thus ends by sculpting the large-scale architecture of the universe. What began as collapse becomes creation of another kind, the formation of order through the inevitability of gravity. Every time a star dies and a black hole is born, the universe deepens its geometry. Each shadow carved into space-time is another reminder that light and darkness are not opposites, but partners in the same cosmic dance. The shadow captured in 2019 is one such product of collapse, frozen in light that spiraled for millions of years before reaching us. Its ring marks the last stable orbit of photons before they fall inward. Its glow comes from matter heated to extremes that no laboratory can replicate. Its darkness represents the continuation of gravity's work, hidden from view, but not from understanding. The story of gravity's collapse, then, is not a tragedy, but a transition, from matter to geometry, from time to timelessness. The black hole stands as nature's simplest yet most complete expression of the laws that govern existence. It reminds us that every star, no matter how brilliant, will one day yield to the same quiet authority of space-time itself. From the ashes of light, gravity writes its signature, a curve so perfect that it holds even against the scrutiny of our finest instruments. And in that perfection lies both the comfort and the mystery, that the universe, no matter how violent, obeys rules of unbroken harmony. Light has always been our messenger from the cosmos. It carries the history of stars, the temperature of galaxies, and the shape of space itself. When Einstein proposed that gravity was not a force, but a curvature of space-time, he changed what that message meant. Light, once thought to move in straight lines through a fixed universe, was revealed to be a traveler obeying geometry. Where mass bends space, light follows those curves. The black hole's shadow is the most dramatic expression of this truth, the visible consequence of invisible geometry. Imagine a beam of light passing near a massive body. According to Newton, gravity would not affect it, for light has no mass. But in general relativity, mass and energy are equivalent, and energy follows the same geometric rules. The path of light, or what physicists call a null geodesic, bends along the curvature of space-time. This bending is what allows us to see gravitational lensing, the distortion of distant galaxies into arcs and rings when their light passes by clusters of mass along the way. The cosmos becomes a hall of mirrors where gravity sculpts images from light. Near a black hole, this bending becomes extreme. The paths of photons curve so tightly that some loop the hole multiple times before escaping. Others fall inward and vanish. The thin, bright ring in the image of Messier 87 is made of photons that almost failed to escape, those that circled the black hole once or twice before reaching our telescopes. Their paths form a sphere of possible orbits, known as the photon sphere, located at 1.5 times the Schwarzschild radius for a non-rotating black hole. Any photon within that sphere is doomed to spiral inward, while those outside may escape, albeit heavily deflected. This geometry of light was not first revealed by observation, but by thought. Decades before telescopes could hope to see such detail, physicists had drawn it on paper. In 1979, Jean-Pierre Luminet used numerical calculations to simulate what a black hole surrounded by an accretion disk would look like. His image, rendered on a computer long before the digital age, showed a bright ring encircling a dark center, with the disk distorted above and below by gravitational lensing. The resemblance to the Event Horizon Telescope's image 4 decades later is uncanny. Illuminate's prediction was based purely on Einstein's equations, mathematics that could trace the journey of light through curved spacetime without ever leaving the page. As computational power grew, others refined the models. In the early 2000s, astrophysicists like Avery Broderick developed detailed simulations of plasma dynamics near black holes, combining magnetohydrodynamics with general relativity. These models predicted not only the ring's shape, but also its asymmetry, the same brightness gradient the Event Horizon Telescope would later confirm. The match between theory and observation was not coincidence, but the result of a century of physics converging on a single truth. Light reveals geometry, and geometry shapes everything we see. To visualize what happens near the event horizon, imagine space as a fabric being stretched downward by mass. A photon traveling across that fabric curves toward the mass, like a marble rolling along a bent surface. But near a black hole, the curvature is so intense that the fabric folds in on itself. The marble no longer rolls past, it falls in, following the contour of spacetime. This is not an analogy, but a geometric reality. The curvature is not in a higher dimension. It is intrinsic to spacetime itself. Every direction that once led away now points inward. The Event Horizon Telescope's measurement of the ring's diameter, roughly 40 microarc seconds as seen from Earth, matched the predictions of general relativity within 10%. To put that precision into perspective, seeing such detail is like reading the date on a coin in Paris while standing in New York. That alignment between theory and data is one of the most extraordinary triumphs in the history of science. It shows that the same equations Einstein wrote in 1915 still describe reality perfectly, even under conditions he never imagined. Light, then, is more than a witness. It is the instrument by which geometry becomes visible. The ring of emission around the black hole is a map of space-time curvature, drawn in radiation instead of ink. Each photon's path encodes information about where and how it was bent. By studying these distortions, scientists can test whether gravity behaves as relativity predicts, or if some deeper theory must replace it. So far, every observation agrees with Einstein's model. No deviations, no cracks, no signs yet of the quantum gravity that must eventually emerge. But even within that perfection lies mystery. The same equations that predict the bending of light also predict the singularity where they fail. The closer light travels to the center, the less we can describe what happens next. At some point, the mathematics run out. The geometry of light ends in a place beyond geometry itself. The interplay of light and gravity is not confined to black holes. We see its echo across the universe, in the arcs of galaxies magnified by invisible dark matter, in the lensing of cosmic background radiation left from the Big Bang, and in the subtle bending of starlight measured during solar eclipses. Each of these phenomena is a smaller version of what the Event Horizon Telescope captured: light obeying the shape of space-time. The shadow of Messier 87, therefore, is not a special case, but the culmination of a universal principle. Light is not merely a tool for seeing the universe, it is the means by which the universe expresses its shape. Every photon carries the curvature of the path it has traveled. The black hole's ring is simply the most extreme version of that truth, the point at which the universe's geometry turns back on itself. If the theory matches observation so precisely, one might wonder what remains hidden. What lies beyond the horizon that light cannot show us? Does the geometry continue inward, or does it fragment into something new? The image of the ring answers one question and asks another. We have seen the outline of Einstein's equations written across the sky, but inside that outline, our knowledge fades into silence. In the space around a black hole, light behaves like a pilgrim on a winding path. Each photon that escapes to the universe beyond has survived a maze of curvature and velocity, deflection and delay. Nothing about its journey is straight or simple. the closer it travels to the horizon, the more time itself seems to slow. From the outside, this delay creates the illusion of permanence, a glow that lingers, as though light has been caught between existence and oblivion. To understand this geometry, we must picture the universe not as a stage upon which objects move, but as a fabric whose weave determines the movement itself. In this fabric, gravity is not a pull, but a tilt. Near massive bodies, the fabric dips, and light, which always follows the shortest possible path, bends around the curve. The more massive the object, the deeper the dip. For a black hole, that dip becomes an infinite funnel. The photons that form the bright ring around Messier 87 are not skimming its surface, but circling along the walls of that funnel, poised between freedom and capture. The path of these photons depends on their angle of approach. Some pass close enough to orbit once or twice before escaping, while others plunge inward and never return. The delicate boundary between those fates defines the edge of the shadow. It is a threshold not of matter, but of trajectories, a contour in space-time itself. This edge is what we see as the boundary of darkness, and it is astonishingly precise. Even a small change in the geometry, if relativity were slightly wrong, would shift that edge and distort the ring. Yet the observed shape holds steady, confirming that Einstein's equations describe reality down to the smallest measurable detail. Gravitational lensing extends far beyond the realm of black holes. When light from a distant galaxy passes near a cluster of galaxies, the cluster's combined gravity bends the light, magnifying and distorting the image. Sometimes this produces multiple images of the same object, or a near-perfect circle called an Einstein ring. In each case, the light acts as a silent tracer, revealing the presence of mass that might otherwise remain unseen. This is how astronomers detect dark matter, not by observing it directly, but by measuring the way it bends the paths of light. Near a black hole, the same principle reaches its extreme. The curvature is so strong that photons from the far side of the accretion disk are bent around the hole, allowing us to see both its front and its back at once. This strange perspective, where light wraps around the void, gives the illusion that the disk stands above and below the shadow, like a glowing halo. In reality, the entire image is a projection, light from every direction converging into the same visual circle. What we call a ring is the imprint of multiple photon paths collapsing into a single view. Every photon that escapes from near the horizon carries information about where it came from and how it was bent. By analyzing their polarization, the direction in which their electric fields oscillate, scientists can map the structure of magnetic fields near the black hole. In 2021, the Event Horizon Telescope released a second image of Messier 87's black hole, this time showing its light as polarized lines curling around the ring. Those lines trace the magnetic fields threading through the plasma, revealing an intricate pattern that channels energy into the giant jets extending from the galaxy's core. The image confirmed that magnetism, not just gravity, plays a crucial role in shaping what we see. In those twisted lines lies another form of geometry, the geometry of fields and flow. Just as mass curves space-time, magnetic fields curve the paths of charged particles, guiding them through the accretion disk and into the polar regions where the jets form. The interplay between gravity and magnetism is delicate. Gravity provides the energy by pulling matter inward. Magnetism provides the structure that directs part of that energy outward. The result is a cosmic engine that converts falling matter into light and motion, its efficiency among the highest known in nature. The bending of light also alters our sense of distance and scale. The ring we see around Messier 87's black hole appears larger than the event horizon itself because the photons we detect have been deflected outward. This magnification is purely geometric, the same kind of distortion that turns distant galaxies into stretched arcs in gravitational lensing. In a way, the black hole acts as its own lens, magnifying the very space that conceals it. The apparent size of the shadow depends on the curvature of spacetime, which in turn depends only on the mass of the black hole. This relationship allowed scientists to measure that mass directly from the image, confirming previous estimates based on stellar motion. When the light of the accretion disk bends so sharply, even time becomes warped. Photons traveling along different paths experience different delays before reaching us. Some arrive slightly earlier, others later, creating subtle interference patterns in the data. The Event Horizon Telescope's correlators, the massive computers that combined signals from around the world, accounted for these differences with astonishing precision. The synchronization had to be accurate to within billionths of a second, or the image would blur into nothing. That precision is not just technological, it mirrors the universe's own precision. The laws governing the motion of light near the horizon are exact, and so our instruments must be equally exact to see them. What all of this reveals is that light is not merely bent by gravity, it is woven into gravity's fabric. Each photon traces a geodesic, a path of least resistance through curved spacetime. And by following those paths, we learn the shape of the cosmos itself. The Event Horizon Telescope did not just confirm that black holes exist. It demonstrated that light is an instrument of geometry, and that geometry is the language in which nature writes its laws. Yet even as this picture fits perfectly, there remains the question of what lies beyond. The photons that form the ring come from outside the horizon. None escape from within. The geometry that shapes their paths stops at the edge of the unknown. Inside, our equations still speak, but they whisper contradictions. There, general relativity predicts infinities, and quantum mechanics demands limits. Somewhere between them must lie the true shape of spacetime, a geometry not yet drawn. In the early 20th century, long before anyone imagined the Event Horizon Telescope, there was a moment when the bending of light first turned from theory into evidence. It happened during a total solar eclipse in 1919. Teams of astronomers, one in West Africa and another in Brazil, set up their cameras to photograph the stars near the darkened sun. Einstein's new theory of general relativity predicted that the sun's gravity would shift the apparent positions of those stars by a small but measurable amount. When the plates were developed, the results matched his prediction almost exactly. Light had curved in space as the theory said it would. That single observation changed physics forever. From that eclipse to the image of Messier 87's shadow, a century of progress unfolded, each step refining our grasp of how light reveals gravity's geometry. The eclipse proved that mass bends light. Gravitational lensing by galaxies showed that this bending could map invisible matter, and the Event Horizon Telescope finally demonstrated that light can orbit gravity itself. These are not separate discoveries, but a continuous thread, evidence that the universe is shaped by curvature at every scale, from the sun's gentle deflection to the violent folding near a black hole. In the simplest terms, the bending of light is the visible sign of spacetime being curved, but at a deeper level, it also reveals how time behaves. For light that travels near a massive body, its path through space and its progress through time are inseparable. The more its trajectory bends, the more time slows along its route. This coupling of space and time is what makes a black hole such a perfect laboratory for physics. Every photon that escapes its grip carries not just information about space, but also about how time itself is distorted by gravity. To an observer far from the black hole, this distortion appears as gravitational redshift. Light climbing out of the gravitational well loses energy, stretching into longer wavelengths. That is why the emission we see from near the event horizon glows in radio waves rather than visible light. The photons began their journey with higher energy, but by the time they reached us, gravity had robbed them of it. What we detect are the long fading notes of a cosmic symphony, played at the threshold between visibility and silence. In numerical simulations, these effects combine to form the same structures we see in the telescope data. The bright ring corresponds to light paths that graze the photon sphere. Inside that ring, the paths cross and terminate. Outside, they diverge and reach us. The result is not a flat picture, but a layered geometry, where each brightness and color shift encodes a distance and a direction in space-time. When we reconstruct the image, we are not capturing an object, but decoding a pattern of delays, intensities, and frequencies, all created by light, navigating the warped fabric around the black hole. Einstein's equations describe this geometry with astonishing precision, but their beauty hides a limitation. They assume that space-time is smooth and continuous. At the scale of quantum mechanics, however, reality might not be smooth at all. If space has a discrete or fluctuating structure, as some theories propose, then light passing near a black hole could carry subtle signatures of that granularity, tiny deviations from the perfect curves predicted by relativity. So far, no such deviations have been observed. The shadow of Messier 87 is perfectly circular within the precision of our instruments. Yet this perfection may be an illusion of scale. We may simply not be able to see the imperfections hidden below our current resolution. For scientists, this balance between perfection and uncertainty is what makes the black hole such a compelling target. It is a place where our two great theories, general relativity and quantum mechanics, must eventually meet. The geometry of light around the shadow is our last confirmed truth before we enter the unknown. Beyond that, inside the horizon, the equations diverge, and new physics must take over. But for now, the bending of light remains our most reliable guide. Gravitational lensing has grown from a theoretical curiosity into a tool that shapes modern cosmology. By studying the way distant galaxies are magnified and distorted, astronomers map the invisible scaffolding of dark matter that threads through the universe. The same principle that curved starlight in 1919 now reveals structures stretching billions of light years. Light continues to show us the shape of the unseen, whether it is a cluster of galaxies or the rim of a black hole. In Messier 87's shadow, we see the geometry of light taken to its limit, the point at which the path of a photon becomes a perfect circle and then disappears. The precision with which this geometry matches Einstein's theory is a testament to how well we understand the universe, and also to how much we still do not. For beyond that circle lies a region that no light can leave and no geometry can yet describe. The image stands as a bridge between the observable and the unknowable. It proves that our equations work where gravity is strongest, but it also frames the boundary where they must one day be rewritten. Each photon in that ring traveled millions of years to reach us, carrying the curve of space within its motion. In their arrival, they tell us that the universe is not built from straight lines, but from gentle bends, continuous and exact, until they vanish into the darkness that geometry itself cannot illuminate. And so, even as we celebrate how light obeys the curvature of space-time, we are left with a quiet question. If light is our only messenger and it stops at the horizon, then what lies beyond? The geometry of light, precise and proven, leads us to the very threshold of understanding, and then ends abruptly at the edge of time. The event horizon is not a wall nor a surface in any ordinary sense. It is a boundary in space-time, defined not by what is there, but by what can never come back. When light crosses it, the possibility of returning to the universe vanishes. The horizon does not destroy, it divides. On one side, events can still influence distant observers. On the other, every future path leads only inward, toward a place that our mathematics still fails to describe. The phrase edge of time is more than poetry. In general relativity, the flow of time depends on gravity. The stronger the gravitational field, the slower time passes relative to regions of weaker gravity. Near the event horizon, this slowing becomes so extreme that to an outside observer, time for the infalling matter appears to halt. From far away, you would never see an object cross the horizon. Its signals would arrive more slowly, their wavelengths stretching until they faded into invisibility. Yet for the object itself, nothing special happens at that boundary. It would cross the horizon without fanfare, unaware that the rest of the universe, now sees it frozen in place. This paradox is one of perspective. Relativity insists that both viewpoints are correct because there is no single universal time. Each observer carries their own clock, their own measure of duration. Near a black hole, those clocks disagree so profoundly that one reality becomes forever disconnected from the other. The horizon is where agreement ends. To describe what happens mathematically, we use the Schwarzschild metric for a non-rotating black hole. It shows how time and space trade roles near the horizon. Outside, we can move freely in space, while time flows forward. Inside, the radial direction becomes as inevitable as the passage of time itself. There is no path outward, because outward no longer exists. This inversion is what makes the horizon such a peculiar and powerful concept. It is not merely a region you can enter, it is a region that rewrites what direction and motion mean. For rotating black holes, the story grows more intricate. The Kerr solution, which describes a spinning black hole, predicts that space-time near the horizon is dragged around by the rotation. This dragging is so intense that anything nearby, even light, must rotate with it. In the ergosphere, the region just outside the event horizon, space itself moves faster than the speed of light relative to distant observers. Nothing can remain stationary there. Yet within this swirl lies a strange opportunity. Because of the rotation, it is theoretically possible for an object to enter the ergosphere, split apart, and send one fragment outward with more energy than it carried in. This process, proposed by Roger Penrose in 1969, shows that the black hole's spin can, in principle, be tapped as a source of energy. The jets streaming from Messier 87's poles may be nature's own version of this extraction, powered not by matter alone, but by spacetime's rotation itself. From the standpoint of observation, we can only see the horizon's influence, not the horizon itself, the ring of light in the event horizon. Telescope's image forms outside that boundary, where plasma still emits radiation before falling in. The darkness at the center is the shadow of the horizon, an optical illusion created by light that missed escape. It marks where time itself folds inward. When scientists measure that shadow, they are indirectly measuring the size of the event horizon. For Messier 87, that radius is about 20 billion kilometers, a vast distance, yet still tiny compared to the galaxy it inhabits. In physical scale, the horizon would fit comfortably within our solar system, but its gravity commands a sphere of influence spanning thousands of light years. The curvature it produces shapes everything from the glowing accretion disk around it to the orbits of stars that dare to come too close. The existence of the event horizon is more than a theoretical prediction, it is a necessity. Without it, the equations describing black holes would lead to contradictions. The horizon is what allows the laws of physics to remain consistent even as gravity reaches its extreme. It is the veil that separates knowable spacetime from the domain where our theories falter. To imagine crossing that boundary is to imagine a journey beyond causality. From the traveler's perspective, time continues as usual. The pull of gravity would feel finite, though increasing with each passing moment. Light from the universe outside would grow bluer and more intense as it falls inward alongside the traveler. Then, as the horizon is crossed, that light would fade. Beyond that point, no message could ever return. The traveler's future ends at the singularity, though to the universe outside, they never quite arrive. This dual reality, crossing in finite time, yet never being seen to cross, is one of the most profound consequences of relativity. It suggests that reality itself depends on the observer's path through space-time. In the same universe, two truths coexist, one in which the fall ends, and one in which it never does. The event horizon. Telescope's achievement lies in showing us the boundary of these truths. Its image is a map of where time slows, where space curves, and where light loses the ability to return. It is not a photograph of destruction, but of division, a portrait of the line where physics begins to change its language. To call the horizon the edge of time is therefore accurate in both poetry and fact. It is where all future paths converge into a single direction, inward. Beyond it, time as we define it no longer measures change, it measures inevitability. Each second, there is not a moment of experience, but a step towards singularity. And yet, to the universe outside, that same moment stretches endlessly. We have never observed the interior of a black hole, and perhaps we never will. But by studying how the horizon shapes light and motion, we can read its outline. The precision of those measurements confirms that the edge of time is not a myth. It is a structure written into the universe itself, a testament to how gravity and time weave together until they become indistinguishable. The horizon stands not as an end, but as an invitation, the ultimate boundary, drawing us closer with questions we are not yet ready to answer. It reminds us that even at the limits of knowledge, the universe remains ordered, mathematical, and astonishingly complete. Near the edge of a black hole, time does not merely slow, it warps into a shape almost unrecognizable from the time we know. Imagine watching a spacecraft approach the event horizon. From far away, its movement would appear to fade, each pulse of its light stretched and reddened until it seems to hover, motionless, forever suspended on the brink. But the people inside that craft would see nothing unusual. Their clocks would tick normally, the horizon would approach, and they would cross it without pause. It is not a trick of vision, but a real difference in how space-time flows for each observer. The closer one moves to the black hole, the more gravity dilates time, until the same second that passes inside becomes countless centuries to those far outside. This distortion is not unique to black holes. It happens everywhere, though faintly. On Earth, time passes infinitesimally faster at the top of a mountain than at sea level, because the gravitational field weakens with altitude. Astronauts on orbiting stations experience slightly slower clocks than those on the ground. We live our entire lives within these shifts, never noticing them because the differences are tiny. But near a black hole, they become monumental. There, relativity stops being a correction and becomes reality itself. Einstein's equations explain this elegantly. They describe space-time as a four-dimensional fabric in which gravity is the curvature caused by mass and energy. The closer you are to that mass, the steeper the curve and the slower the flow of time. The event horizon represents the ultimate slope, where the fabric folds so completely that all future paths point inward. To move forward in time inside the horizon is to move closer to the singularity. Outside, time still has room to turn. Inside, it is a one-way descent. The idea that time can flow differently for different observers might sound abstract, but it has been tested countless times. Atomic clocks flown on aircraft, satellites orbiting Earth, and signals from the Global Positioning System all confirm time dilation to extraordinary precision. Without accounting for relativity, GPS receivers would drift by kilometers each day. The laws that govern our everyday technology are the same laws that govern the fate of light near a black hole. The difference is only one of scale. In the environment around Messier 87's black hole, the difference becomes cosmic. The gas spiraling in the accretion disk experiences time so slowly that its motion, though rapid locally, appears to us as a near-static glow. What looks like a still ring in the Event Horizon Telescope's image is a time-averaged picture of plasma moving at nearly the speed of light, frozen by relativity into a steady halo. The black hole's gravity not only bends space, it stretches time itself into a lens that turns motion into permanence. For physicists, the horizon is also where causality, the sequence of cause and effect, begins to change its meaning. In the ordinary universe, one can trace a chain of events forward, with each cause leading to an effect that might be observed elsewhere. But inside the horizon, that chain terminates. All causes lead inward, and no effect can influence the world outside. It is as if the future of the black hole is disconnected from the rest of space-time. This is why the horizon is more than a physical boundary. It is a boundary of communication, of interaction, of knowledge. Rotating black holes complicate this picture even further. Their spin drags space around with them, twisting the geometry so that even light that tries to move against the rotation is pulled along. The region where this dragging becomes irresistible is called the ergosphere. Within it, all objects must rotate in the same direction as the black hole. Yet paradoxically, this region also allows energy to escape. A particle entering the ergosphere can split, with one fragment falling into the black hole and the other escaping with more energy than it had before. The process does not violate physics. It borrows energy from the black hole's rotation. Over cosmic timescales, this exchange may slow the spin, converting rotational energy into radiation that escapes into space. In Messier 87, the immense jets of plasma that extend thousands of light years from the galaxy's center may be powered by such effects. Observations show that magnetic fields near the black hole twist in alignment with its rotation. These fields act like cosmic wires, channeling energy outward. The result is a continuous stream of matter accelerated to near-light speeds, glowing across the electromagnetic spectrum. These jets prove that the horizon, while it traps matter and light, can also drive the release of energy beyond anything our machines could produce. The horizon's physics blends stillness and violence. To an outside observer, the black hole appears calm, defined by a simple geometry. But at its edge, the interplay of gravity, magnetism, and motion becomes a storm of energy. It is there that space-time itself vibrates, generating gravitational waves when two black holes merge or when matter plunges inward unevenly. These ripples travel across the cosmos, carrying information about the most violent events in existence. They are echoes of the horizon's motion, the music of curved space-time ringing across millions of light years. And yet, despite this perfect description of the horizon's behavior, the question of what happens inside remains unanswered. General relativity predicts that beyond the horizon lies a singularity where density becomes infinite. But infinity is not a physical quantity. It is a signal that the theory has reached its limit. Somewhere before that point, the smooth fabric of space-time must give way to something granular, something quantum. What that something is, no one yet knows. For now, the horizon is the line where our knowledge ends and imagination begins. It is a boundary that both confirms and challenges general relativity, a region where time dilates, causality bends, and the geometry of the universe reveals its most intricate design. The Event Horizon Telescope has shown us the edge of that line in unprecedented detail, turning what was once a theoretical boundary into a measurable phenomenon. And yet, the horizon's mystery remains intact. We can describe everything that happens just outside it: the bending of light, the slowing of time, the structure of magnetic fields. But the instant the horizon is crossed, our equations fall silent. Time stops not because the universe ends, but because our understanding does. Inside the event horizon, space and time exchange their roles completely. What was once distance becomes duration, and what was once the steady rhythm of time becomes a direction that cannot be turned back. No traveler could avoid the singularity any more than you can choose to stay in one moment forever. Each tick of the clock is a step deeper inward, and that inward journey is written into the geometry itself. There is no stopping, no hovering, no escape. From the outside, none of this can ever be witnessed. Light that begins its climb outward from just within the horizon finds space itself streaming in the opposite direction, faster than any signal can travel. This is not motion through space, it is the motion of space. The horizon is a one-way membrane, allowing entry but forbidding return. In a very real sense, it defines the limits of causality. What happens beyond its surface cannot influence the rest of the universe, and yet the mass, the rotation, and even the charge of what falls in still shape the geometry outside. That paradox, information apparently lost but gravity still preserved, is one of the deepest puzzles in physics. It lies at the heart of the modern search for a unified theory that can reconcile general relativity with quantum mechanics. If the black hole truly destroys all details of what falls into it, then the basic principle of quantum theory, that information can never be lost, must fail. But if information is somehow preserved, it must be encoded in a way that our current understanding cannot yet decode. In the 1970s, Stephen Hawking added another twist. By combining quantum field theory with the curved geometry of space-time, he showed that black holes should not be completely black. Quantum fluctuations near the event horizon would create pairs of virtual particles. One particle could fall inward, while its partner escaped to infinity, carrying away a tiny amount of energy. To conserve energy, the black hole itself must lose mass. Over immense timescales, it would gradually evaporate. This radiation, Hawking radiation, meant that the horizon was not the final silence we once imagined. It whispered photons into the void, turning the black hole from a perfect absorber into a faint, dying ember. But Hawking's discovery made the paradox sharper. If the black hole evaporates completely, what happens to the information encoded in what fell inside? Quantum theory insists it must be preserved, yet general relativity provides no mechanism for its return. This contradiction, known as the information paradox, remains one of the great unsolved problems in physics. Many proposals have been made. Perhaps information is stored on the horizon itself as a kind of hologram. Perhaps it leaks out with the radiation in scrambled form. Or perhaps space and time are woven in ways we cannot yet describe. None of these explanations has yet been proven. The event horizon is thus more than a physical boundary. It is a frontier between our two greatest theories. On one side lies relativity, continuous and geometric, describing the curvature of space-time. On the other lies quantum mechanics, discrete and probabilistic, describing the behavior of particles and fields. At the horizon, these two worlds meet and conflict. The smooth geometry demanded by Einstein meets the restless uncertainty demanded by quantum law, and neither can completely describe what happens there. Observations continue to tighten the frame around this mystery. The Event Horizon Telescope confirmed that the outer geometry behaves exactly as relativity predicts. Gravitational wave observatories, detecting the final mergers of black holes, have shown that the ringing patterns of space-time match Einstein's equations perfectly. These successes leave no doubt about what happens outside the horizon, but they also deepen our curiosity about what lies within. We know the shape of the border precisely, yet we do not know what the border contains. Some physicists imagine that deep inside, the singularity may not exist at all. Instead, quantum effects could replace it with something finite, a region where space-time becomes granular, where geometry itself is quantized into tiny loops or strings. In such models, collapse may halt at a smallest possible scale, turning what we call a singularity into a new form of matter or energy. Others propose that the interior connects to another region of space-time, perhaps even another universe, though no evidence yet supports such conjectures. These are not fantasies but mathematical explorations born of the same equations that predicted black holes in the first place. Still, without observation, they remain untested. The horizon, then, stands as the perfect metaphor for knowledge itself. It is the line beyond which we cannot yet see, but which continues to shape everything we can observe. The curvature outside tells us something must be hidden within. Every photon bent around it, every ripple of gravity passing by, carries the imprint of what lies beyond. We learn about the invisible by measuring its influence, and in that way, we glimpse the boundary of understanding. When we look at the image of Messier 87's shadow, we are not just seeing a black hole. We are seeing a question framed in light. What happens to space, time, and information when they cross the edge of time? The answer is written somewhere beyond the horizon, in a language our physics has not yet learned to speak. For now, the horizon endures as both truth and mystery. It is the edge of time, the boundary of knowledge, and the meeting point of the two greatest ideas humanity has ever created. On one side, geometry. On the other, quantum uncertainty. Between them, a ring of fire circling silence. In the middle of the 20th century, black holes were puzzles of geometry. By the end of that century, they had become puzzles of information. The shift began when physicists realized that if black holes truly swallowed everything that crossed the event horizon, light, matter, and all traces of their inner arrangement, then something fundamental about the universe might be broken. Information, in the quantum sense, was not supposed to disappear. It could transform, scatter, or hide, but never vanish completely. The question was simple to ask and nearly impossible to answer. When a black hole devours matter, does it also erase the information that defines it? To understand the problem, we must first recall what information means in physics. Every particle carries measurable properties: position, momentum, charge, spin, the details that together describe its state. The laws of quantum mechanics say that these properties evolve predictably over time. Even when particles interact, the combined information remains conserved. If we knew the complete state of the universe at one moment, we could in principle reconstruct its state at any other, forward or backward in time. This principle, called unitarity, is one of the cornerstones of quantum theory. But a black hole seems to violate it. When something falls beyond the event horizon, all that remains visible is its total mass, electric charge, and angular momentum. Every other detail, the shape of the object, its composition, its quantum correlations, disappears. To an outside observer, the black hole looks the same no matter what fell in. Two black holes of equal mass and spin are indistinguishable, even if one formed from gas and the other from collapsing stars. Physicists summarize this stark simplicity with the phrase, "black holes have no hair." For a while, this simplicity was seen as elegance rather than trouble. Then came Stephen Hawking's discovery in 1974. By applying quantum field theory to the curved geometry of space-time, Hawking found that black holes are not entirely dark. Quantum fluctuations near the event horizon continually create pairs of virtual particles. Normally, these pairs would annihilate each other instantly, returning their borrowed energy to the vacuum. But near a black hole, one particle can fall inward while the other escapes to infinity. To a distant observer, it appears as faint thermal radiation, now called Hawking radiation. This revelation changed everything. If black holes radiate energy, they must gradually lose mass. Over vast timescales, they would shrink and eventually evaporate completely. Yet Hawking's calculations showed that the radiation was purely thermal, meaning it carried no information about the material that had fallen in. If the black hole disappears and the information encoded in its contents never emerges, then the principle of unitarity is violated. The universe would lose information. A crime against the foundation of quantum theory. At first, many accepted that perhaps information truly could be destroyed, that black holes were exceptions to the quantum rule. But as decades passed, most physicists grew uneasy. If information can vanish here, why not elsewhere? The loss would spread uncertainty across the entire framework of physics. Laws that rely on determinism would crumble. Something deeper had to be wrong with the picture. One clue came from an unexpected direction: thermodynamics. Hawking's result implied that black holes have a temperature, and thus an entropy, a measure of disorder or information content. In 1972, before Hawking's work, Jacob Bekenstein had already proposed that a black hole's entropy is proportional to the area of its event horizon, not its volume. Each unit of surface area corresponds to a tiny bit of information, suggesting that whatever falls into the hole is somehow recorded on its boundary. Hawking's radiation confirmed that idea, establishing the famous Bekenstein-Hawking formula: entropy equals 1/4 of the horizon's area, measured in fundamental units of Planck length squared. This relationship led to one of the most profound insights in modern physics. The universe might be holographic. The holographic principle, proposed independently by Gerard 't Hooft and Leonard Susskind in the 1990s, suggests that all the information within a volume of space can be represented by data encoded on its boundary, much like a hologram stores a three-dimensional image on a two-dimensional surface. In this view, the black hole's event horizon is not a featureless void, but a cosmic screen containing every detail of what has fallen in, scrambled beyond recognition, but not lost. The idea gained powerful mathematical support from Juan Maldacena's ADS-CFT correspondence, formulated in 1997. This theory describes how a type of gravitational system existing within a curved spacetime can be exactly equivalent to a lower-dimensional quantum field theory on its boundary. Gravity and quantum mechanics, long at odds, might be two faces of the same reality. Within this framework, information is never truly lost. It is simply rewritten on the horizon in a different language. Yet even these elegant theories cannot yet be tested directly. Hawking radiation from astrophysical black holes is far too weak to detect with current instruments, and we have no observational proof that it carries or preserves information. For now, the paradox remains suspended between mathematics and evidence. The shadow we see in the Event Horizon Telescope's image marks the place where this debate plays out. A border not just of light, but of knowledge itself. Physicists continue to explore new possibilities. Some suggest that the horizon might behave like a quantum membrane, storing information temporarily before releasing it through subtle correlations in the outgoing radiation. Others propose that space-time near the horizon might be far more complex than classical relativity predicts, its surface seething with quantum activity. A few even imagine that what we call the interior could be an illusion created by the information encoded on the boundary, that there is no inside as we traditionally conceive it. Every idea points toward the same underlying question. Can physics describe a universe in which information truly survives the edge of time? The answer will decide whether quantum theory and general relativity can ever be reconciled. The information paradox is not just a mathematical puzzle. It is a mirror held up to our understanding of reality. If information is preserved, the universe is ultimately knowable, its laws reversible and exact. If it is lost, then something fundamental about causality and predictability fails. The shadow of a black hole, glowing faintly at the edge of darkness, is the frontier where that decision will one day be made. In the years after Stephen Hawking first described black hole evaporation, the question of information became one of the most heated debates in theoretical physics. It was not a quarrel about numbers, but about reality itself. Hawking argued that once a black hole radiates away, the information about everything it consumed is gone forever. To him, the radiation's purely thermal nature meant that no trace of the original matter could survive. The laws of physics, he proposed, might simply allow information to be destroyed. This conclusion, however, struck at the very heart of quantum mechanics. For Niels Bohr, Erwin Schrödinger, and the generations who followed them, the universe had always been a perfect ledger. The probabilities might shift, the wave functions might collapse, but the sum of all information was eternal. To lose it would be to admit that the universe forgets. That idea felt almost sacrilegious to quantum physicists, and a chorus of disagreement arose. Among the most vocal critics was Leonard Susskind, who refused to accept that black holes could erase the past. The argument spanned decades, carried out in papers, conferences, and thought experiments. Susskind and others began to see the event horizon not as a place of destruction, but as a surface of storage. Information, they proposed, was not lost within the black hole, but smeared across its boundary. The interior, we imagine, might be a kind of holographic illusion, a projection from the information encoded on the surface. This idea became the foundation of what is now known as black hole complementarity, the notion that to an outside observer, information never actually crosses the horizon, while to the infalling observer, it does. Both views are consistent, yet neither can witness the other's truth. Over time, evidence began to favor this reconciliatory view. The mathematics of quantum field theory in curved spacetime suggested that subtle correlations might exist in Hawking. Radiation. Faint patterns carrying traces of what fell in. If true, then the radiation would not be perfectly random. It would be entangled with the remaining black hole. As the hole shrinks, these correlations could, in principle, release the encoded information back into the universe, albeit in a form so scrambled that recovery would be almost impossible. This subtlety lies at the core of the so-called Page curve, named after physicist Don Page, who in the 1990s calculated how the entropy of Hawking radiation should evolve over time if information is preserved. According to his result, the entropy should first rise as the black hole radiates thermally, but eventually it must fall again, returning to zero as the information escapes in the later stages of evaporation. Decades later, in 2019 and 2020, theoretical breakthroughs in quantum gravity confirmed that this behavior could indeed emerge from fundamental principles. Using mathematical constructs called quantum extremal surfaces, researchers showed that the Page curve naturally appears in calculations that treat spacetime and information as deeply intertwined. These results do not yet solve the paradox completely, but they show that the universe may keep its memory after all. What makes this revelation extraordinary is how it reshapes our view of reality. It suggests that spacetime itself may be a manifestation of information. The geometry we experience as distance and duration could arise from the entanglement patterns between quantum bits. The horizon in this picture is not a physical barrier, but a limit on how information is organized. When we speak of the black hole's surface area corresponding to its entropy, we are measuring how many quantum degrees of freedom are needed to describe its state. Every square of Planck length on the horizon could represent one fundamental unit of information, a cosmic pixel in the universe's ultimate display. This perspective extends beyond black holes. If information truly underlies spacetime, then everything, stars, galaxies, even the expanding universe itself, might be an emergent phenomenon born from quantum entanglement. In this view, general relativity and quantum mechanics are not rivals, but partners, describing the same reality at different scales. The holographic principle provides the bridge. What appears three-dimensional may be encoded on a two-dimensional surface somewhere at its boundary. For black holes, that surface is the event horizon. For the universe as a whole, some physicists speculate the cosmic horizon created by the speed of light may play a similar role. In both cases, what we see as space and time could be the shadow of a deeper informational order. The black hole's paradox thus becomes not just a question about lost data, but a clue that the universe itself might be made of information. Despite the elegance of this idea, direct evidence remains out of reach. Hawking radiation from astrophysical black holes is far too faint to detect, and no experiment yet can probe the quantum microstructure of spacetime. Still, the theory has gained strength through consistency. Every attempt to model black holes in ways that respect both relativity and quantum mechanics now seems to point toward the same conclusion. Information is preserved, though hidden in ways we do not yet understand. Hawking himself eventually changed his mind. In 2004, at a conference in Dublin, he presented a revised argument suggesting that black holes might indeed return information through subtle correlations in their radiation. The universe, he conceded, does not forget. The admission was quiet but monumental, closing a philosophical loop that had lasted 3 decades. Yet even that reconciliation leaves deeper questions. If the horizon stores information, how is it encoded? Is spacetime fundamentally digital, with quantum bits woven into its geometry? Or is it continuous, with information flowing in patterns too intricate to describe? These are questions that no telescope can yet answer. They belong to a realm where thought experiments still guide us more than instruments can. The event horizon. Telescope's image of Messier 87 does not show Hawking radiation or the quantum foam of the horizon, but it does reveal the context in which these questions exist. It shows that the horizon is real, that its geometry behaves as relativity predicts, and that the shadow we see is not the end of understanding, but its beginning. The faint light around that darkness is our only experimental window into a problem that unites the smallest and the largest scales of existence. For now, the information paradox remains unresolved in practice, though theory leans toward preservation. It stands as a reminder that our deepest laws are connected, that gravity, light, and information are threads of the same fabric. The black hole, once a symbol of oblivion, now appears as a vault of memory, holding the story of everything it has consumed, written in a code we are only beginning to decipher. And so, the paradox is no longer just a question of loss. It has become a question of translation, of how information survives its journey through the edge of time, and how we might one day read it back from the light that escapes. The story of the black hole leads inevitably to a point where mathematics itself begins to tremble. General relativity, a theory celebrated for its elegance and precision, predicts a place inside every black hole where its own logic breaks down. At that place, known as the singularity, the curvature of space-time becomes infinite, and the known laws of physics lose their meaning. It is a point not in space, but in understanding, the boundary where equations end and mystery begins. To see why this happens, we must return to Einstein's field equations, the foundation of general relativity. These equations describe how mass and energy determine the curvature of space-time, and in turn, how that curvature directs the motion of matter. For almost every situation, from planets orbiting the Sun to galaxies rotating across cosmic scales, these equations work with exquisite accuracy. But when the density of matter becomes too great, the mathematics predicts that curvature will grow without limit. The gravitational field becomes infinite. Space-time itself folds into a point where its geometry cannot be extended further. In 1939, J. Robert Oppenheimer and Hartland Snyder studied what happens when a massive star exhausts its nuclear fuel and collapses under its own gravity. Their calculations, the first of their kind, revealed that the collapse does not stop. Once the star passes a critical radius, there is no pressure strong enough to counteract gravity. The equations drive the collapse to a singularity. From the perspective of an external observer, time slows infinitely as the surface approaches the event horizon. But from the star's own perspective, the collapse continues inexorably until space-time itself ends. For years, many physicists regarded the singularity as a sign that the model was incomplete rather than a feature of nature. Even Einstein himself doubted that such infinities could exist in the real world. Yet in the 1960s, the British physicist Roger Penrose changed that view forever. He developed a mathematical proof known as the Singularity theorem, showing that under very general conditions, any object collapsing under gravity will form a singularity. The result did not depend on symmetry or special assumptions. It was a fundamental property of Einstein's equations. Penrose's insight was later expanded by Stephen Hawking, who applied similar reasoning to the universe as a whole. If gravity could compress stars into singularities, perhaps the entire cosmos began as one, a point of infinite density from which space and time expanded. Thus, the mathematics that describes the interior of a black hole also describes the origin of the universe. The singularity is not an exception. It is a common thread running from the smallest scales of collapse to the birth of everything. But infinities are not physical quantities. They are the mathematical equivalent of warning lights, signs that a theory has reached beyond its domain of validity. When general relativity predicts infinite curvature, it is not describing something tangible, but confessing its own limits. The theory that united space and time into a single geometric fabric cannot by itself describe what happens when that fabric tears. To move further, physics needs a new framework, one that includes the quantum nature of matter and the graininess of space-time itself. This is where quantum gravity enters the story. In quantum mechanics, uncertainty is built into every measurement. Energy and position, momentum and time can never be known with infinite precision. When this principle is applied to gravity, it implies that space-time cannot be continuous at the smallest scales. Instead, it may consist of discrete units, tiny loops, or vibrating strings that resist infinite compression. At scales near the Planck length, about 10 to the power of minus 35 meters, the smooth geometry of general relativity may give way to something granular. In such a universe, singularities might not exist at all. Loop quantum gravity is one such attempt to describe this regime. It treats space-time as a network of finite loops, interwoven like threads in a cosmic fabric. According to this theory, the gravitational field is quantized, and the curvature of space-time cannot exceed a certain maximum value. Collapse may continue until these quantum effects become dominant, at which point gravity itself turns repulsive, preventing the formation of an infinite singularity. The result is a bounce rather than a breakdown, a transition to another phase of space-time, perhaps even another universe. String theory offers a different vision. It proposes that the fundamental building blocks of nature are not point-like particles, but tiny one-dimensional strings whose vibrations create all known particles and forces. In this framework, the singularity may be resolved because the strings cannot be compressed to a true point. Their finite size smooths out the infinities that plague general relativity. In certain models, what appears as a singularity in classical physics becomes a dense but finite region of highly curved space-time, governed by the rules of quantum mechanics. Although these ideas remain theoretical, they share a common message. The singularity is not the end of reality, only the end of classical description. The black hole's interior is not a void, but a realm where quantum and gravitational effects merge. We do not yet have the complete theory to describe it, but every clue points to the same direction, that the fabric of space-time is richer, stranger, and more resilient than the equations of Einstein alone can reveal. Numerical relativity has brought us closer to this frontier. Using supercomputers, scientists can now simulate the mergers of black holes and track the resulting gravitational waves with unprecedented precision. These simulations confirm that general relativity holds under conditions of immense curvature right up to the formation of the horizon. The waves detected by observatories such as LIGO and Virgo match the predictions almost exactly. But the interior, the singularity itself, remains hidden behind the horizon, beyond both observation and simulation. We can trace the approach, but never the arrival. The singularity, therefore, remains the universe's deepest secret, a place where time and space lose their separate meanings, and where the familiar distinction between cause and effect dissolves. It is a reminder that even the most successful theory in science carries its own horizon, a boundary beyond which it cannot see. What we call a singularity might one day be revealed as a new kind of order, a domain where geometry becomes quantum, where space-time itself fluctuates, and where information, rather than mass or energy, becomes the true currency of the cosmos. Until then, the singularity is both a mathematical necessity and a philosophical challenge, whispering that the universe, for all its precision, still hides something beyond comprehension. In the search for what truly happens at the heart of a black hole, science has reached a point where observation must yield to imagination guided by mathematics. The singularity remains forever hidden, cloaked by the horizon, yet its existence shapes everything around it. To study it is to read a shadow of a shadow, to infer the unseen from the way space and time behave near their limits. For many physicists, the singularity problem is not simply a question of what lies inside, but of how to construct a theory that does not break there. General relativity gives us the curvature of space-time, while quantum mechanics gives us the fluctuations of matter and energy. Each theory works flawlessly in its own domain, but where gravity becomes as strong as quantum effects, near the Planck scale, both sets of rules demand attention and neither can dominate. The mathematics of this union, called quantum gravity, is still unfinished, but each new insight brings the singularity into sharper conceptual focus. Loop quantum gravity imagines space-time as a lattice of interconnected loops, each representing a quantum of area or volume. At normal scales, these loops are unimaginably small, so space appears smooth. But when collapse drives matter to densities near the Planck limit, the loops resist further compression. In this picture, a black hole's interior might reach a state where gravity turns repulsive, reversing the collapse before an infinite singularity can form. The core could rebound into another expanding region of space-time, what some have called a white hole. This rebound is not speculation for its own sake, but a direct consequence of the equations when the geometry itself is quantized. It suggests that every black hole could be the seed of a new universe, branching invisibly from the old. String theory approaches the problem from another direction. It replaces point-like particles with one-dimensional strings, whose vibrational modes correspond to different particles and forces. Because strings have finite size, they cannot shrink to a point, and thus the singularity may be replaced by a dense but finite configuration of energy. In certain solutions, black holes become fuzzballs, tangled webs of strings and brains whose collective behavior mimics the properties of a classical black hole from afar, but with no true singularity inside. Each fuzzball would store the information of what fell into it on its surface structure, resolving both the singularity and the information paradox at once. These frameworks remain mathematical, yet their implications are profound. They suggest that the interior of a black hole may be more like a phase of matter, a state where gravity, quantum mechanics, and thermodynamics all intertwine. At the boundary between these regimes, concepts such as distance and time lose their classical meaning. What replaces them might be an abstract network of relationships, the geometry of information itself. In recent years, gravitational wave astronomy has given physicists a way to test gravity where it is strongest. When two black holes spiral together and merge, they generate ripples in space-time that carry away immense energy. These waves encode the entire history of the collision, how the horizons stretched, twisted, and fused. By comparing the observed signals with numerical simulations, scientists can confirm how space-time behaves under extreme conditions. So far, every observation has matched Einstein's predictions. No deviations, no signs of new physics, only the steady rhythm of relativity's perfection. Yet even that perfection is suspicious. The fact that our measurements match the equations so well implies that the singularity, if it exists, must be hidden flawlessly. General relativity describes everything we can see, but none of what we most wish to know. It is as if the universe has arranged things so that the breakdown of the theory is forever concealed behind the horizon. In this sense, the cosmic censorship conjecture, proposed by Penrose, remains intact. It states that singularities, if they exist, are always hidden from external view. Nature, it seems, protects its deepest secrets with geometry itself. Still, hints of deeper structure may lie in the details. Some physicists have proposed that as black holes merge, quantum effects at their horizons could leave faint imprints, tiny echoes in the gravitational wave signals. These would appear as delayed repetitions of the main pulse, caused by reflections from a quantum-structured surface rather than a perfect event horizon. The search for such echoes continues. None have been confirmed yet, but instruments are growing more sensitive, and the idea is not beyond testing. If detected, these signatures would mark the first direct evidence of quantum gravity, proof that the horizon is not the final curtain, but a porous veil through which the laws of the very small and the very large finally meet. The singularity's mystery also echoes in the earliest moments of the universe. The equations that describe the collapse of a massive star are mathematically identical to those that describe cosmic expansion in reverse. In both cases, space-time curves so sharply that classical physics breaks. If the Big Bang was once a singularity, perhaps it too was softened by quantum gravity, replaced by a big bounce emerging from a prior universe. The death of a star and the birth of a cosmos could be two faces of the same process, gravity closing one space-time while opening another. Such symmetry appeals to the human sense of order, but it also underscores how limited our understanding remains. Whether the singularity is replaced by strings, loops, or something entirely new, we know only that infinity itself cannot be physical. Somewhere between 0 and infinity lies the truth, a description of reality that unites quantum behavior with the curvature of space. For now, the mathematics serves as our telescope. Equations become the lenses through which we glimpse what cannot yet be observed. The singularity problem is no longer about a point of infinite density, but about the relationship between knowledge and its limits. Just as an event horizon hides the interior from view, the boundary between classical and quantum theory hides the full structure of space-time from comprehension. Each time we refine the mathematics, we push that horizon back a little further. And though the singularity itself may forever remain unseen, its existence has already transformed physics. It has forced us to confront the edges of our theories and to accept that even the most complete ideas can carry their own boundaries. The singularity is the silence that follows when mathematics has said all it can, and the universe quietly continues beyond. To grasp the meaning of the singularity, one must accept that it is not a place, but a condition, a moment when the known structure of space-time ceases to exist. Near this boundary, gravity grows stronger than any force, density surpasses any imaginable limit, and time itself loses its ordinary order. The equations of general relativity, perfect everywhere else, begin to diverge. Their solutions no longer describe a universe, but dissolve into infinities. What lies beyond those infinities may not be destruction, but transformation. Modern physics treats this transformation as the ultimate test of its unification. The singularity is where quantum theory and general relativity must finally meet. Both are correct within their own domains. Relativity governs the vast and smooth, quantum mechanics rules the small and uncertain. The singularity exists precisely because we try to apply one without the other. It is the point where geometry, continuous and deterministic, must become discrete and probabilistic. In the mathematics of numerical relativity, scientists now simulate gravitational collapse with extraordinary precision. Using grids of billions of points and equations evolved over supercomputer time, they follow how matter curves spacetime and how that curvature feeds back upon itself. The simulations can trace the formation of the horizon, the merger of black holes, and the emission of gravitational waves. But as the curvature intensifies near the center, the numerical solutions fail. The values blow up, not because the computer is wrong, but because the theory is silent. No coordinate system, no variable change, no approximation can tame the singularity. In every calculation, there comes a point where numbers lose meaning. The silence that follows is the mathematical echo of the event horizon's darkness. Some researchers attempt to bridge that silence using semi-classical approximations, applying quantum corrections to relativity without a full quantum gravity theory. These models predict that before the singularity is reached, quantum pressure may counteract gravity's pull, creating a finite core. The collapse halts not in infinity, but at a Planck-scale density, forming a kind of quantum star. To the outside world, it would appear indistinguishable from a classical black hole, but but its interior would be stable, compact, and extraordinarily dense. If Hawking radiation continues, the object might eventually evaporate, leaving behind a tiny remnant, a fragment of the original black hole, storing its information indefinitely. Another possibility arises from the idea of space-time duality, in which the interior of a black hole could be mathematically mapped to another, lower dimensional system. According to this reasoning, the singularity is not a rupture in physics, but a change of perspective. The inside and the outside may be two descriptions of the same information, encoded differently depending on the observer's frame. In such a view, singularities do not destroy information, they translate it. Gravitational wave observatories have begun to hint at what might one day test these concepts. Each merger event they record carries data about how horizons behave just before fusion. When two black holes collide, their individual event horizons stretch and merge in less than a second, forming a new horizon that rings and settles. The final waveform, the ring down, tells us how quickly space-time returns to equilibrium. Thus far, every observation matches Einstein's predictions perfectly. Yet if quantum structure lurks beneath, future detectors might detect deviations, extra frequencies, faint echoes, or irregular damping that cannot be explained by classical physics. If such deviations appear, they will mark the first experimental evidence of quantum geometry. There is a deeper, more philosophical symmetry hidden here. The equations describing gravitational collapse and those describing cosmic expansion are mirror images of each other. Run time forward and you see the birth of a universe. Run it backward and you see the death of a star. The singularity is the pivot between these opposites, the moment where endings and beginnings converge. Some cosmologists propose that the Big Bang was not a true singularity, but a transition, a bounce from a prior universe collapsing through its own horizon. If so, then every black hole might serve as a kind of cosmic womb, creating a new region of space-time beyond its singularity. From outside, we see only darkness. From within, an entirely new universe could be unfolding. No evidence yet confirms this idea, but it reflects an enduring pattern in physics. What appears as catastrophe in one description often becomes creation in another. The singularity, once thought of as a failure, may turn out to be a bridge. Whether that bridge connects one side of the same universe or leads to another is a question that will demand both mathematics and imagination to answer. Even as we search for these answers, we must remember how far the mathematics has already taken us. We can now simulate the formation of black holes, measure their masses from gravitational waves, and even photograph the outline of their horizons. The only thing we cannot yet describe is the final step, the moment where geometry collapses into something new. In that sense, the singularity is not a flaw in our equations, but a challenge written into them, reminding us that every description of the universe contains its own horizon of knowledge. Perhaps the singularity endures because nature itself insists on boundaries. Just as an event horizon hides the interior of a black hole from view, the singularity hides the next layer of reality from theory. Beyond it may lie the quantum texture of space-time, the true architecture upon which relativity and quantum mechanics are both built. The singularity is not a hole in physics, but a doorway, one that opens only when the two greatest ideas in science finally become one. If the black hole's shadow represents the edge of sight, then the singularity represents the edge of thought. It is the point where reason and wonder meet, where equations stop, but curiosity continues. And like the horizon that conceals it, the singularity's purpose may be to remind us that even the deepest darkness in the universe is a frontier, not a finish. The universe reveals itself as a vast and intricate structure, a cosmic web of matter and light stretching across billions of light years. Galaxies cluster along filaments of invisible dark matter, forming a pattern that resembles the neural network of a colossal brain. Within this immense web, Black holes serve as gravitational anchors, stabilizing galaxies and orchestrating their growth through time. From the faintest dwarfs to the luminous giants like Messier 87, every galaxy appears to carry a dark heart at its center. It was not always known that such monsters existed everywhere. In the mid-20th century, astronomers found that stars near galactic centers moved faster than expected, hinting at massive unseen objects. In the Milky Way, careful tracking of stellar orbits in infrared light finally exposed the truth. An invisible body, 4 million times the mass of the Sun, confined within a region smaller than our solar system. The only possible explanation was a supermassive black hole. Similar findings soon followed in other galaxies. The speeds of stars, the shapes of orbits, and the energetic emissions from active galactic cores all pointed to the same conclusion. Supermassive black holes were not cosmic anomalies, but central components of galactic evolution. Observations revealed a striking correlation. The mass of a galaxy's black hole is proportional to the velocity dispersion of its stars, a relationship now known as the M-sigma relation. This link suggests that galaxies and their central black holes grow together, each influencing the other through feedback cycles of energy and gravity. When a black hole feeds, it becomes one of the brightest objects in the universe. Gas drawn toward the event horizon forms a swirling accretion disk, heated by friction and magnetic turbulence to temperatures of millions of degrees. The radiation released can outshine the combined light of billions of stars. Some of this energy escapes along magnetic field lines as narrow relativistic jets that shoot across intergalactic space. These jets, moving at nearly the speed of light, can stretch for hundreds of thousands of light years, depositing energy into the gas that surrounds the host galaxy and regulating its future. The black hole thus acts as both destroyer and creator. The same forces that consume matter also shape the birth of new stars. In some galaxies, the heat and radiation from an active nucleus drive gas away, halting star formation. In others, the shock waves compress clouds of matter, triggering stellar birth. On the grand scale, this process balances galaxies between activity and rest, keeping their growth self-regulated through cosmic time. Observations with the Chandra X-ray Observatory and the Hubble Space Telescope have shown the scars of these interactions. In galaxy clusters like Perseus, enormous cavities appear in the X-ray emitting gas, bubbles carved by jets from central black holes. These cavities rise buoyantly through the cluster atmosphere, spreading heat and preventing gas from cooling too quickly. Without them, clusters would collapse under their own radiative losses. The black holes, by releasing only a fraction of their gravitational energy, maintain the thermodynamic balance of entire clusters. Simulations of the universe, built from first principles of physics, confirm this role. Models that include only gravity and gas produce galaxies too massive and bright. When the effects of black hole feedback are added, the simulated cosmos matches observation. The delicate balance between inflow and outflow, accretion and radiation, creates galaxies that live and evolve as we see them today. The James Webb Space Telescope has recently extended this understanding to the dawn of time. It has found quasars, intensely luminous galactic cores, shining when the universe was less than 1 billion years old. Their black holes already weigh more than 1 billion suns, raising questions about how such massive objects could have formed so early. Some may have begun as direct collapses of primordial gas clouds, skipping the stage of stellar birth. Others may have grown rapidly through mergers in the dense environment of the young cosmic web. However they formed, their light rionized the universe, ending the cosmic dark ages and making space transparent. From the faint glow of the earliest quasars to the quiet hum of galaxies today, black holes have been the architects of structure. Their gravitational pull gathers matter, while their radiation sculpts it. Without them, the universe would be a less organized place, more diffuse, less luminous, and without the elegant hierarchy we observe. In their darkness, the geometry of the cosmos finds its center, To see a black hole was once considered unattainable. These objects, defined by their invisibility, seemed beyond the reach of any telescope. Yet science thrives on the tension between impossibility and curiosity. By the early 21st century, advances in radio astronomy and computational imaging made the idea conceivable. If we could link telescopes across the planet, synchronizing them into one vast array, we might resolve the light orbiting the very edge of a black hole's horizon. This vision became the Event Horizon Telescope, or EHT, a global network of observatories working together to form a single Earth-sized instrument. Using a method called very long baseline interferometry, the EHT combined signals from sites thousands of kilometers apart. Each telescope recorded radio waves at a wavelength of 1.3 millimeters, synchronized by atomic clocks accurate to within billionths of a second. The data were stored on specialized hard drives and flown to central processing centers, where supercomputers correlated the signals to reconstruct the image. In April 2017, 8 observatories, from Chile's Atacama Desert to Hawaii's Mauna Kea, from Arizona to Antarctica, turned their gaze toward 2 targets: Sagittarius A star at the heart of the Milky Way, and the immense black hole in Messier 87. The larger one, 6.5 billion solar masses, offered a steadier view. After years of analysis, the data revealed a ring of light encircling a central darkness, the first direct image of a black hole's shadow. When the image was unveiled in April 2019, the world paused. The golden ring, faintly asymmetric, matched Einstein's predictions almost perfectly. Its size and shape confirmed the curvature of space-time around a rotating black hole, providing the most precise test of general relativity ever performed. What appeared on screens across the world was not a photograph in the ordinary sense, but a reconstruction of radio waves bent by gravity, transformed into visible form through mathematics. Behind that single frame lay years of engineering and calibration. Every atmospheric fluctuation, every delay in signal, every instrumental drift had to be corrected. The reconstruction algorithms, developed independently by multiple teams, converged on the same image, ensuring that what we saw was not artifact, but reality. The EHT's achievement was more than technical, it was philosophical. It turned the entire Earth into a single eye, synchronized by human cooperation. The telescope stood on different continents, in different time zones, under different skies, yet all observed the same object at the same instant. The project united scientists across cultures and disciplines, creating a planet-wide laboratory for gravity itself. 3 years later, in 2022, the collaboration revealed its second image: the black hole at the center of our own galaxy. Smaller and more turbulent, Sagittarius A star flickered as plasma orbited its horizon. Yet when averaged over time, the result mirrored the earlier image almost exactly. 2 different black holes, 2 vastly different environments, 1 consistent geometry. The same theory of spacetime held true across scales of 1,000,000 to 1. The future of this effort is already taking shape. The next generation Event Horizon Telescope will add more stations around the globe, filling gaps in coverage, and observe at multiple frequencies simultaneously. The goal is not just to capture still images, but to record movies, to watch plasma flow, magnetic fields twist, and hotspots orbit the shadow in real time. Space-based interferometers are also under study, promising even higher resolution. One day, we may image the jet base of Messier 87 directly, tracing how magnetic energy transforms into motion. What began as an impossible dream has become a new branch of astronomy, one that does not look at objects, but at the curvature of space-time itself. The EHT has shown that even the most extreme regions of the universe can be rendered visible when technology and theory converge. The image of the black hole is not an end. It is the first sentence in a new language of observation, written in the grammar of light, bent by gravity. The ring of light surrounding the black hole's shadow is more than an achievement of observation. It is a statement about the nature of knowledge. The bright edge we see is all that the universe allows us to know directly. Beyond it lies a region where the familiar laws of physics break down, a domain still ruled by equations we have not yet written. The shadow is not a solid object, but a projection of absence. It marks the set of photon trajectories that cannot escape, the boundary between light that survives and light that falls forever inward. Within that outline lies the event horizon, the point of no return where escape velocity equals the speed of light. For an external observer, time slows infinitely as matter approaches that limit. For the matter itself, time continues normally, crossing the horizon without pause. Two realities coexist, each true within its own frame, yet separated by relativity. The image confirms that Einstein's geometry works perfectly at the edge of visibility. The ring's diameter, brightness, and asymmetry all align with prediction. But this success also exposes what remains unknown. General relativity tells us how space-time curves. Quantum theory tells us how energy behaves. Neither can yet describe what happens when both dominate. Inside the horizon, those two frameworks collide. The result is the singularity, a place where density and curvature reach infinity and our mathematics fail. Some physicists believe that the singularity is not real, but a sign of theory's incompleteness. Quantum gravity, when discovered, may replace the singularity with something finite, perhaps a bounce, perhaps a core of quantum geometry. Others propose that information falling into the black hole is preserved on its surface, encoded holographically in the horizon's area. If so, the smooth darkness we see may be a two-dimensional library of everything that has ever crossed it. The Event Horizon Telescope cannot yet reveal these details. Its image shows only the outermost layers of reality, the light still able to escape. Yet that limitation is itself profound. The shadow is the first scientifically defined horizon of ignorance. It is the measurable shape of what we do not yet know. What the image hides, then, is not emptiness, but order, an order beyond our current reach. The black hole's shadow marks the threshold where physics becomes philosophy, where observation becomes imagination, disciplined by mathematics. The same geometry that bends light at the edge of Messier 87 also governs the birth of the universe and the structure of space-time everywhere. The black hole is not a cosmic monster, but a cosmic mirror. It reflects the unity of creation and destruction, showing that gravity's greatest collapse can coexist with the universe's greatest order. Its shadow does not hide chaos, it hides deeper simplicity, the logic that connects everything. When we look at that image, we are not seeing darkness. We are seeing the limit of light, the final expression of relativity, the frontier of what it means to know. The photons that circle the horizon are ancient messengers, carrying proof that even in the universe's most extreme silence, law and structure remain. One day, perhaps, we will see past the shadow, through quantum theory, through gravity unified with the microscopic. But even then, another horizon will appear, farther out, another boundary calling us forward. The pursuit of knowledge is endless, precisely because the universe allows it to be. The black hole's shadow is not the end of curiosity, it is its shape. It is the outline of the unknown, drawn in light around the abyss, reminding us that even where no light escapes, understanding can still expand. The darkness hides no myth, no supernatural force, only the frontier of physics itself, a frontier brightened by the glow of discovery.